We'd like to welcome our next presenter, is Dr. Daniel Duke, and he's a senior lecturer in the Department of Mechanical and Aerospace Engineering at Monash University in Australia. He holds a Bachelor of Engineering and Aerospace Technology and a PhD in Engineering also from Monash University. His area of expertise is in fluid mechanics of aerosols and sprays with a particular focus on pressurized metered dose inhalers, happily for us. His current research interests span both experimental and simulation-based approaches for complex multi-phase component fluid flows. So with that, over to you, Daniel.
Thank you very much for the generous introduction. I couldn't have asked for a better segue in the schedule. So John has just made a very, very powerful case for the need to switch propellants in MDIs. And what I'm here to briefly tell you today is that switching propellants means redesigning the actuator for the MDI. And doing that means that we need new tools to do that and to do it quickly. And I'm hopefully here to give a little glimmer of hope today and to show you some of the novel methods that we're using to do that. And I'd like to acknowledge all my co-authors, especially Ben Myatt and Phil Cox from Condiva, who've been really very strongly supportive of our research at Monash University. So computer modelling is the topic that I'm going to focus on mostly, and computer modelling of inhalers and performance of aerosols has been done for decades, but most of the focus has been on regions where the flow is very dilute, the oropharyngeal region, the upper airway. Joe Cam had an outstanding article in Inhalation magazine recently on this exact topic, which I encourage you to read. In terms of state-of-the-art, the cutting-edge research, there's a lot of work going on now at modelling aerosol deposition in the deep lung tissues, but what I'm interested in is the actuator, where it all begins. What's going on here? The problem is that modelling this region requires an entirely different class of computer models, entirely different methods, and we're developing those. To give you a little taste of the complexity of what's going on in an MDI, we can have a look at this image here. And if we zoom in on the actual orifice where the liquid comes out, in the top right there is an X-ray high-speed image that we took a couple of years ago of an MDI spray. I think it's HFA-152a solution formulation. And something very interesting is going on here, which is really hard to model or simulate or predict. Flash atomization. The fluid is superheated. There can be a 50-degree difference between its boiling point and the temperature, and this causes the fluid as it comes out of the nozzle to explosively vaporize, forming small droplets, which is great for MDI performance, but very difficult to model and capture. We also have complex evaporation and mixing processes, and finally precipitation of particles. And this depends on the entrainment of warm ambient air into the spray, also quite difficult to model. Now, I'm not going to spend much time on this slide because John has just made a very powerful case for the need to switch to the new propellants. But there is a technical challenge here. If we look at all these numbers here, these numbers determine the way that this new propellant is going to behave when it first comes out of the actuator orifice, and these numbers all change, and that means that this flashing process changes, the droplet formation process changes. We can ask some questions here. How will performance change with these new propellants? And most importantly, what I'm here to hopefully show you today is that we can accelerate the design process by doing in silico testing, that is, simulating in the computer before we move to in vitro testing, to find new designs and promising avenues, perhaps evaluating propellants against one another more quickly than we can in the lab. Now, I'm not here to bore you with maths, so I'm going to skip over the complicated bits. I'm happy to take questions on it. But the special model that we've developed for doing this is called a homogeneous relaxation phase change model. And we're solving these nasty equations here. This is basically just conserving mass, momentum, and energy. It's just Newton's laws expressed in a more complicated way. We're also introducing a new feature in our computer model, which is called a non-equilibrium phase change model. And this is what sets it apart from a lot of one-dimensional models that you see. What we're allowing the fluid to do in our computer models now is depart from its thermodynamic equilibrium state. It takes a little time when the fluid comes out of the actuator orifice for it to notice that the pressure has changed and to respond to that, and this model captures that. We also model with extra equations the way that the warm, humid air mixes into the spray, And when it comes to modelling the droplets themselves, we don't capture every individual single droplet because that would just be computationally infeasible. Instead, what we do is we simply ask the question, in any part of our computer model, how many droplets are there and what's their total surface area? And from that, we can derive a Sauter mean diameter and some aerodynamic properties. It's an approximation, but it works really well. However, there is a problem. There is a computational challenge. No matter how sophisticated your model is and no matter how clever you are, you run up against mathematics. And we run into this thing called the Friedrichs Louis condition, which gives people, like engineers like me, nightmares. This equation tells you how long your simulation is going to take. If we want to simulate the orifice, the velocities of the fluid coming out of the orifice can, at that instant, be extremely high, not for long, but in an instant, about 80 metres a second. And if we want to resolve the flow around the orifice to predict how it's going to behave, we need a grid that resolves down to about 15 or so micron. And if you crunch the numbers, that means that every time you solve the entire problem, you only move forward a few hundred nanoseconds in time. And that means that you need to do this millions of times, and the amount of computer power required is immense. And for this reason, these models of MDI actuator orifices have really not been economically feasible. But things are changing. We have two sort of tricks we can apply to this problem. One of them is that we can be smart about our model and we can throw away some physics and throw away some resolution in the areas where it doesn't have a great impact on the results. We're not after 100% perfect accuracy, we're after 99%. We just want to get close enough, and some things you can throw away and still get very close results. The other thing we do is we use a really powerful computer. We use supercomputers like these ones in Australia and the United States shown here. And what that does is it takes a calculation that would take on your very best desktop computer you could buy today about a year, and it brings it down to 1 to 2 days. And for a really big case, maybe a week. And this is what makes this go from something that's just an academic exercise to something that's actually a useful tool for device design. So our results look something like this. We can model through the spray its velocity, its temperature, its density, and measure all kinds of things that you can't easily directly obtain in the lab. In order to capture all this turbulent mixing that you get in the spray, we use something called large eddy simulation, which models the very small scales that we don't care about so much. And we used NIST databases to get all our ChemPhys props. Now, there's a problem with this model. It looks nice, but can you trust it? If you have a computer model, you have to prove that you can trust it. One of the questions is, as I make my resolution higher and higher and higher, and my model gets better and better, does the result change or does it not change? It better not depend on the quality of my grid. And what we find is that with our simulations, we can get most of the properties we need down to better than 1%, which is fantastic. And the only thing that really sticks out is this orange line here. That's the Sauter mean diameter. So if we're willing to get a Sauter mean diameter prediction to within 10 to 15%, of course the model is good, but then we need to run a more expensive one to double check that it's actually accurate. We also need to compare against experiments because a model that doesn't match with the real world data is a useless model. So here's a prediction from the computer about what an optical extinction measurement of an MDI spray would look like. This is inside the mouthpiece, by the way. We're within a few millimetres of the orifice. And if we overlay it with a measurement taken in our lab in Australia, the spray angle and width match really well. And we can do it from different points of view, different magnifications, and we get similar results. That's nice, but we can go one better. We've developed a whole lot of X-ray based measurements that can give you quantitative measurements, and if we cut a slice out, we can compare the actual model, which is the red line, to the X-ray, which is the blue dots, and again, it matches really well, so we're pretty confident. One of the fascinating things you get out of these models that we didn't know before is the flow does some strange things. HFA-152a actually almost goes supersonic when it comes out of the nozzle. It's not normal supersonic flow like a fighter jet. It's not that we're going really fast, it's that the speed of sound gets really low because the fluid is very cold. This actually helps break up this liquid and create smaller droplets. When we go to the new propellants, HFO-1234 or HFA-152a, that effect goes away quite significantly and we see it bump up the droplet size. So this sort of physics that's helping us is actually starting to be diminished. We can also predict the droplet size distributions. The dashes there are a Malvern spray tech measurement in the lab, and those spiky lines are the computer predictions. And we get slight increases in droplet size, and the computer model predicts those median values very well. When we want to know why the droplets are getting bigger with the new propellants, we can look at the computer model and we can see. It turns out that for the new propellants, there tends to be a core region of poorly atomized droplets in the middle. You get this rich core that hasn't mixed well. And so this tells us that we just need to redesign the actuator to try and suppress that effect. So now we know why they're getting bigger and we can do something about it. The other thing we see is that with the new propellants, HFA-152a in particular gives you a less stable spray. It tends to wobble about a bit, which is interesting. And 1234 gives you a very dense, long spray. This is going to change the targeting of the spray. It's going to change the amount of deposition in the throat. And this is something that we need to think about as well. All right, so what can we do about it? Could we manipulate the aerosol or the spray properties by changing the orifice? We've run dozens and dozens of computer models with different orifice shapes and sizes. And what we found is the good news is yes, within reason, within the sort of region of parameters we're looking at, you can change the diameter and the length of the orifice, and you can tune up and down, for example, the width of the plume to whatever you want, which is really nice. This is promising. This suggests that redesigning the actuator orifice means you can tune it to get equivalence if you want or to hit a particular value. So what does the future hold for these sort of computer modelling approaches? Computational fluid dynamics is nice. It can predict some pretty hard to measure properties, gives you some hints into what the underlying physics are doing inside the aerosol where it's hard to measure. The trends between the new and the old propellants match very well with our experiments, and we have a poster here on the experimental work, and I'd encourage you to come and have a look at it if you want to learn more about the experimental work. What we also find is that the main factors driving the performance of the spray close to the actuator orifice are the orifice shape, the physical chem properties, of course, but also the near orifice mixing environment. There are some things that really just depend on that turbulent mixing with the warm air, not the orifice. So the environment outside is more important than the environment inside. And this is something that we have to think about in device design. What the CFD allows us to do, these computer models, is to cheaply do large parameter searches at very low cost and low risk. We can just shoot for the moon and try something crazy, come up with any orifice actuator design or shape or size that we want and just see what happens at very low cost and risk. However, I would give a word of caution in concluding there will always be a need for experiments. Sometimes people are tempted to say to you, soon computers can do everything and you won't need the lab anymore. This is nonsense, because an experiment is only as good as the laboratory data that confirms that it is actually following reality. So a word of caution. But this can really accelerate the design process, and I think that within the next 5 to 10 years, we're going to see some very exciting developments in computer modelling. So with that, I'll finish, and I'd be happy to take questions. Thank you.
So do we have any questions for Danielle? There we are. I can see somebody down there.
Jason Suggett from Trudell Medical. Great presentation, really good science, and this is, with the greatest respect, maybe a challenge. What's the application for this? Just because I've seen data already in fine particle mass where I've used the same actuator with 134a salbutamol and 152a, and the fine particle mass is pretty similar. Probably could argue clinically similar. So we just heard that we want to get the products to market as soon as possible. So how would you use the modeling to actually accelerate? Do you think it would enable in Europe to go with just in vitro only and avoid a PK? Because if you need a PK, you need a clinical. I would argue let's just get to the clinical studies as quick as possible.
Oh, thank you for the question. No, look, I generally agree with what you're saying here. Where these models provide acceleration is in the process of designing new actuator orifices and doing that work. So if you decide that that's not necessary and you want to skip ahead, then sure, I agree with you that that's the way to go. But when it comes to, for example, demonstrating equivalence for certain parameters to do with the spray or the aerosol, for example, its width or its structure, its droplet size distribution, perhaps if you have the time to do that, at that stage of the work, that's the part that it accelerates.
Thanks.
Can I ask?
Anyone else?
Yes, over there. Sorry, the lights are very poor here. So you can really raise your hand, and if the mic people can raise their hand as well.
Hardik Shah, Covis Pharma. Thanks very much. It's great that you touched on the environmental aspect towards the end slide to understand the modeling aspect. At the same time, for the pMDI, the patient inhalation, the warm air, the disease stage, that also further propels the particles into the deep lung. Can that be, have you considered that, or that would be another 2 or 3 PhDs do you need to do the work? Cheers, thanks.
Thank you. Yes, yes, that is work for the future for other PhD students, perhaps. We are considering things like the temperature and humidity of the ambient environment, but if we want to think about what's happening in the airway, what we do is we take the outputs of a model like this and couple it up with the inputs of a DEM, a discrete element model, which would do a better job at predicting that kind of thing. So what we can give is the initial conditions accurately to a model that then simulates the flow in the airway if we want to consider, for example, the stage of disease or how the airway affects the outcomes.
Super, great. So thank you all right, quick question, quick answer over there.
Okay, thanks for that. Very quick. Will Ganny from Nanofarm. Does your model handle non-volatiles? Can you look at solutions or suspensions?
We're working on that right now, so you can come and chat to me about it later, but that's current work, yes.
I will do. Thank you.
Thank you.
Excellent. Thank you very much. Super. Thanks.